In this lesson, we're going to learn about geometric sequences and series. All right, so a geometric sequence, which is also called a geometric progression, is a sequence where each term after the first is obtained by multiplying the preceding term by a fixed non-zero real number known as the common ratio. So you can hear that throughout today's lesson. We will use a lowercase r to represent our common ratio. All right, let's look at a very simple example. So suppose we have the geometric sequence where your first term, or a sub 1, is 1, then the second term, or a sub 2, is 3, then a sub 3 is 9, a sub 4 is 27, a sub 5 is 81, and then we have the 3 dots to say the pattern continues forever. If you look at this, I want you to notice that we're just multiplying by 3 to get to the next term. So the idea here is that the r, that common ratio, is going to be 3. In other words, I start with 1. So that's my first term. That's my a sub 1. So a sub 1 equals 1. Then if I want to get to the second term, I'm just going to multiply by 3. So in other words, a sub 2 is equal to 1. That's your a sub 1 value times 3. That's your r, and that equals 3. So that puts me right here. Then when I think about my a sub 3, what I'm going to do is, again, I'm just going to multiply 3, my a sub 2 value, by 3. So notice down here, the way I have this written, so a sub 3 is equal to 3. Again, that's my a sub 2 value, times 3, that's my r, and that equals 9. So then if I want a sub 4, again, I'm just going to multiply by 3. So I'm going to have 9 times 3, which gives me 27. So coming down here, a sub 4 is equal to 9. That's my a sub 3 value, times 3. Again, that's my r, and that equals 27. Let's just do this one more time. So here we're going to a sub 5 now. So we're going to multiply by 3 one more time. And let me fix that 3 and make it a little bit better. So 27 times 3 would give me 81. And again, just coming down here, your a sub 5 is equal to 27. Again, that's the a sub 4 value times 3. That's the r, and that equals 81. And again, you can continue this. So I think we all know that if we wanted a sub 6, this equals what? What's the a sub 5 value, which is 81, times 3, that's your r, and that equals 243. And then if you wanted a sub 7, that equals what? So 243, that's your a sub 6 value, times 3, which equals 729. Again, and so on and so forth. In the previous example, we sort of eyeballed things to figure out the common ratio r, but there's an official formula you can use. So to find r, our common ratio, we can use the following formula. Essentially, you have r is equal to a sub n plus 1 over a sub n. So in other words, this right here is one more than this right here. And all this is you're going to pick any two consecutive terms. So that means they're going to be next to each other. So in your geometric sequence, you're going to divide the rightmost term, so that's the one with the higher index value, by the leftmost term to get the common ratio r. So if I come back up here, again, if I wanted r without eyeballing it, you could pick any two terms that are next to each other. So you could pick a sub 1 and a sub 2, and you could just divide a sub 2 by a sub 1. So you could say that r is equal to a sub 2 over a sub 1, which is 3 over 1, which equals 3. Okay, we'll look at a quick example of this. I think this is pretty straightforward. So suppose you're given the geometric sequence where your a sub 1 is negative 4, a sub 2 is negative 24, a sub 3 is negative 144, a sub 4 is negative 864, and then again, the pattern continues forever. Well, again, if you wanted to find r, the common ratio, what you're going to do is pick two terms that are next to each other, and then you divide the guy on the right by the guy on the left. That's all you have to do. So for this one, I'm going to do a sub 2 over a sub 1, and that equals negative 24 divided by negative 4, so that's going to be 6. Again, you could also pick any other two terms that are next to each other. So as another example, here r is equal to a sub 4 over a sub 3, so that equals negative 864 divided by negative 144. So again, that's going to give me 6 either way. All right, so in this section, most of the problems are going to be quite simple. You're just going to use this formula. In some cases, you have to do some basic algebra. You might have to create a system of equations or something like that, but overall, it's not too bad. The idea here is we're going to use this formula to find the nth term. So whatever it is, let's say you wanted a sub 10, where you just plug in the information you're given, and that'll give you a number. You might also be asked to find the explicit formula, so the a sub n for that given situation, but it's pretty straightforward. So a sub n is equal to your a sub 1 times r raised to the power of n minus 1, and coming up with this formula is quite simple. It's very similar to what we saw in the last lesson when we talked about arithmetic sequences. So here we're going to start off with the fact that a sub 1 is just a sub 1. So a sub 1 equals a sub 1. Then for a sub 2, this is a sub 1 times r. Again, this is the common ratio. And then for a sub 3, this is equal to a sub 2 times r. Forget about this stuff for right now. I'm just going to go down. For a sub 4 is equal to a sub 3 times r. And then for a sub 5, you could say it's a sub 4 times r. For a sub 6, you could say it's a sub 5 times r, so on and so forth. The way we're going to end up with this right here is we're going to make a little substitution. So right here, you'll notice that where it says a sub 3 equals a sub 2 times r, you notice I have some additional stuff over here. And all we're doing is we're saying, well, a sub 2 is equal to this. So this right here is a sub 1 times r. So in the place of a sub 2, I'm just going to plug in. In other words, this right here is getting plugged in for a sub 2 right there, which means it goes right there. So what you have is times r here. So this right here is going to go right here. So if I look at the way that it's written now, it's a sub 1 times r, which is a sub 1 times r squared. Now I want you to stop for a moment and notice that this index right here, which is 3, is going to be 1 more than the exponent right here, which is 2. If we look down here, let me actually erase all this. If we look down here, we're going to see what the pattern is going to be. So for a sub 4, it equals a sub 3 times r. Well, again, I just said that a sub 3 can be written as a sub 1 times r squared. So that is going to go in for a sub 3 right there. So this right here is going to go in right there. And again, it gets plugged in right there, so it's going to be right here. So if you look at what's left, it's going to be this times r. And again, this is times r. So you're going to end up with a sub 1 times r cubed now, because r squared times r is r cubed. Now again, I'm going to call your attention to the fact that, let me actually erase this so this is more clear. This right here, this exponent, is 1 less than this index here, which is 4. This establishes a pattern to where when we continue down, you see a sub 5 equals a sub 1 times r to the 4th power. So this right here is 1 less than this right here. A sub 6 is equal to a sub 1 times r to the 5th power. This is 1 less than this right here. And then we can just say that a sub n is equal to your a sub 1 times r to the power of n minus 1. So if this right here is n, then this right here is 1 less, so it's just n minus 1. Okay, let's look at some typical examples. So these are pretty easy overall. We just want to look at the geometric sequence we're given. And in this case, a sub 1 is equal to 1, a sub 2 is equal to -2, a sub 3 is equal to 4, a sub 4 is equal to -8. And then again, we have the 3 dots to say the pattern continues forever. And we want to find a sub 9 and then a sub n. Well, again, the formula we're working with is a sub n is equal to a sub 1 times r raised to the power of n minus 1. Okay, so looking at things, do we have a sub 1? Yes, because it's just the first term. This right here is a sub 1. So you can say a sub 1 is equal to 1. So that's going to get plugged in right there. But we're not ready to do that yet. I'll do it on the next page. We have to figure out what r is. And again, we know how to do that from our formula. Pick any two terms that are next to each other. So I could pick a sub 1 and a sub 2. I think that's pretty easy to do. And then you divide the one on the right by the one on the left. So we're going to say that r is equal to a sub 2 over a sub 1, which equals -2 over 1, which equals -2. And again, you can check this. So 1 times -2 is -2. -2 times -2 is 4. 4 times -2 is -8. Again, if you get something, I would just check it really quickly, just to make sure you didn't make a simple error. So that means the r value is -2 and the a sub 1 value is 1. All right, so coming down here, now we're just going to plug into the formula. So if we're trying to figure out what a sub 9 is, what equals a sub 1, in this case, that's going to be 1, so just plug in. Then your r is -2, so plug that in there. So that's going to go right there. A word of caution here, make sure in this section that you're always using parentheses when you get an r value that is negative. That is super important. So the only thing left to do is to figure out the exponent here. And again, we say that it's 1 less than whatever the index is. If this is n, this is n minus 1. So if this is 9, this is going to be 8 because 9 minus 1 is just 8. Once you have this, you can just key it into the calculator. So 1 times anything is itself. So you really just need to do -2 to the power of 8, which gives you 256. Again, make sure this is wrapped in parentheses so you get this answer. In terms of a sub n, the explicit formula, all you have to do is replace what you can. So you're going to put a 1 in for a sub 1. Since 1 times anything is itself, you could leave this off. Although a lot of teachers like you to write it like this when 1 is your a sub 1 value, just simply so it matches the formula perfectly. But it would be okay if you wrote a sub n is equal to just the -2. That's your r value raised to the power of n minus 1. And where this comes in handy is if you have, let's say, a question, let's say it asks for something like a sub 12. Well, all you have to do is just plug in. So you just say that this is equal to -2 raised to the power of, we know 12 minus 1 is 11, and just key this into the calculator, and that would give you -2048. So if you have a few of these you need to do, calculating the explicit formula first is probably the way to go. All right, let's take a look at another example. So here we have a sub 3 is equal to 48, and then a sub 6 is equal to -3072. We're asked to find a sub 9 and then also a sub n. So again, in this particular situation, we need to figure out what a sub 1 is, and we need to figure out what r is. But the problem is we don't have a sub 1 directly. We don't have the first term like we did in the last problem. And we also don't have two terms that are next to each other, so we can't use that formula to calculate r. So what can we do in this situation? Well, all we're going to do is plug in and create a system of equations. There's other ways to do this, but this is probably the easiest one to understand. So essentially, what you're going to do is you're going to plug in. So we know a sub 3. So a sub 3 is equal to a sub 1 times r squared. And again, if this is a 3, this is a 2. Then you have a sub 6 is equal to a sub 1 times r to the 5th power. Since this is a 6, this is a 5. So all you're going to do is plug in for a sub 3. So a sub 3 is equal to 48. And then we're going to plug in for a sub 6. So that's equal to negative 3072. Again, just information we got from the previous page. And then coming down here, we just set up our system of equations. So equation 1 is a sub 1 times r squared equals 48. Again, this is your a sub 3 value. And then equation 2, a sub 1 times r to the 5th power. This is equal to negative 3072. Again, this is your a sub 6 value. What I would do here is divide equation 2 by equation 1. That's perfectly legal as long as a sub 1 is not 0 and r is not 0, because you would be dividing by 0 and that's undefined if either one of those was 0, but that's not going to be the case here. So this is perfectly legal to do. So let's go a sub 1 times r to the 5th power divided by a sub 1 times r squared. And this equals negative 3072 divided by 48. Okay, so going through, this is going to cancel with this. A sub 1 over a sub 1 is 1. And then r to the 5th power over r squared. So this is going to cancel with this, and this would be r cubed. So the left side here is just r cubed. And this equals, on the right side, negative 3072 divided by 48. If you key that into a calculator, you're going to get negative 64. All right, at this point, you can just solve the equation for r. Now remember that if you had something like x cubed equals negative 64, we talked about the fact that you would have one real solution there and then two non-real complex solutions. But we don't need the non-real complex solutions. We just need the real solution. So for this one, we could just take the cube root of each side. So let me say that we have the cube root of r cubed is equal to the cube root of negative 64. And so this right here is going to cancel with this right here. And you're going to have r is equal to the cube root of negative 64 is going to be negative 4. So now I have my r value. And what I'm going to do is plug back in to the first equation of the system. So remember, we had a sub 1 times r squared is equal to 48. Well, if I know that r is negative 4, just plug that in for r. And what this gives you is negative 4, again, this is wrapped. So negative 4 squared is going to be 16. So this is 16 times a sub 1 is equal to 48. And I'm just going to divide both sides of the equation by 16. This would cancel. And what I'm left with is a sub 1 is equal to 48 divided by 16 is going to be 3. So at this point, I know that a sub 1 is equal to 3 and r is equal to negative 4. So now I have the information I need to plug in. So again, we go back to this formula and you plug in a 3 for a sub 1. So that goes right there. You're going to plug in a negative 4 for r. So that goes right there. And essentially, if you want a sub 9, this just equals 3 times. You have your negative 4, make sure to wrap that in parentheses, raised to the 8th power. And this is an exponent of 8 because this is an index of 9. This is always one less than this. And if you key this into the calculator, you're going to get 196,608. Again, for the explicit formula, plug in a 3 for a sub 1, plug in a negative 4 for r, and then basically you would have a sub n is equal to, you just have your 3 times this negative 4, make sure to wrap it in parentheses, raised to the power of n minus 1. So this formula, again, if you had a lot of things that you wanted to calculate, you would do this one first. If it's just one, then you could do it after. It doesn't really matter. All right, let's talk about the sum of the first n terms of a geometric sequence. So at this point, we know that a series is the sum of the terms of a sequence. So to be specific here, a geometric series is just going to be the sum of the terms of a geometric sequence. If we have something like S sub n, this is used to denote the sum of the first n terms of a geometric sequence. This is known as the nth partial sum and can be found using the following formula. Now I'll show you where this is coming from in a moment. For right now, let's just read through the formula. So S sub n is equal to, you have your a sub 1 times the quantity, 1 minus r to the power of n. This is over 1 minus r. And of course, we don't want r to be equal to 1 because if you plugged in a 1 there for r, you would have 1 minus 1, which is 0, and division by 0 is undefined. All right, let me show you where this comes from. So it's not that bad overall. So you have S sub n here. So this means sum the first n terms of your geometric sequence. Again, if you have something like a sub 1, and then you would have a sub 2, which is a sub 1 times r. And then a sub 3, again, can be written as a sub 1 times r squared. Again, just following where this is 1 less than this, like we talked about earlier. And then, you continue this pattern, you're going to get to sum a sub n. So let's say this continues. And this equals a sub 1, and then times r raised to the power of, again, this would be 1 less than this. So this is n minus 1. So when you sum these guys together, you get a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus the pattern continues plus a sub 1 times r raised to the power of n minus 1. Again, just matching this. Okay, let me get rid of this. Now what we're going to do is produce this second equation, or you could say the bottom equation. And the way we're going to get that is we're going to multiply both sides by r. So if I multiply s sub n times r, I get r times s sub n. And then over here, a sub 1 times r is a sub 1 times r. A sub 1 times r again would be a sub 1 times r squared. Again, this would continue. This one over here multiplied by r, let me write that out so that's not confusing. So a sub 1 and then times r raised to the power of n minus 1 and then times an r there. Well, this would be a sub 1 times, you would have r, the common base would stay the same. Let me write a visible 1 here. This would be to the power of n minus 1 plus 1, and minus 1 plus 1 goes away. So that's where you get this a sub 1 times r to the power of n. So the right side just becomes a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r cubed plus pattern continues plus a sub 1 times r to the power of n. Now what we're going to do is subtract the top equation minus the bottom equation. Or in other words, you could say you're subtracting the bottom equation or the second equation away from the first. So on the left, you're going to have s sub n minus r times s sub n. So that's this right here. This equals on the right. You can see that this is going to cancel here. A sub 1 times r minus a sub 1 times r, that's gone. Then similarly, this is going to cancel. All these terms are going to cancel, and this is going to cancel. So really all you're left with is this a sub 1 minus this a sub 1 times r to the power of n. So that produces this right here. All right, so at this point, we're just going to factor out the s sub n from the left side. So that comes out here. So s sub n times the quantity 1 minus r, and this equals. On the right side, we're going to have this a sub 1 that we can factor out. And so this is times the quantity 1 minus r to the power of n. Okay, let me slide down here. All we have to do at this point is divide this side by the quantity 1 minus r, and divide this side by the quantity 1 minus r. And let's cancel this with this. So a common factor of 1 minus r. So this is going to be s sub n is equal to a sub 1 times the quantity 1 minus r to the power of n. And this is over 1 minus r. And of course, I'm going to put my restriction in here. We don't want r to be 1. If r is 1, then you have a special case, which I'm going to talk about in a moment. But essentially, you want to say where r is not equal to 1. All right, for the special case where r is equal to 1, then every term in the sequence is equal to a sub 1. So what do I mean by that? So let's say I gave you a geometric sequence where every term was 3. So let's say 3, and then 3, and then 3, and then I'm just going to keep doing this for a while. And then I'll stop and I'll say that the pattern continues. Well, my a sub 1 value is 3, my a sub 2 value is 3, my a sub 3 value is 3, and so on and so forth. So my common ratio, my r here, is just going to be 1. So r in this case is equal to 1. Okay, well, if r is equal to 1, again, if you plug into that previous formula, you're going to get division by 0, which is undefined. So what you have to do is think about this a different way. So let me box this off and just say that s sub n here, let's just say we wanted s sub 4. This would be equal to what? What's the sum of the first 4 terms? So it's 3 plus 3 plus 3 plus 3. So 3 plus 3 plus 3 plus 3. And that is equal to 12. The other way to do it, again, is just to use this here. So s sub 4 is equal to, well, what is the n value here? Well, the n value is 4. So I'm going to go 4 times, what's the a sub 1 value? Well, that's 3. And again, that works because if r is equal to 1, every term in the sequence is equal to a sub 1. So it's just 4 times 3, which is going to be 12. So in the off chance that you get something like this, it's usually a trick question or something like that, then this is how you want to solve it with this formula here. Okay, let's look at an example. So we're going to do this with the summation notation. Remember, we talked about this before. So this is read as the sum as I goes from 1 to 8 of this 3 times you have negative 2 raised to the power of I minus 1. So where students get confused here is going to be the different letters involved. Remember that I is called the index of summation. So this is nothing more than just a counter. It tells me I'm starting when I is equal to 1. Plug that in there. 1 minus 1 is 0. Negative 2 to the power of 0 is going to be 1. So you get 3 times 1, which is 3. Then I plug in a 2 for I, then a 3, then a 4, then a 5, then a 6, then a 7. And then when I get to this 8 right here, that's the upper limit of summation, I stop. So when we go to this formula down here, you'll notice that I want a sub 1, I want r, and I want n. That's what I need. Well, this n right here, remember, I'm told that I want to sum the first n terms of that geometric sequence. Remember, when I look at summation notation, this tells me where I stop. It's the upper limit of summation. So that is going to be my n value. So you're going to have to remember that. So n is equal to 8. I know it causes a lot of confusion because when you look at all these formulas, all the letters are changing around constantly. We have the a sub n is equal to a sub 1, then times r raised to the power of n minus 1. So there might be some confusion with this n and this n. But again, when you look at this right here, just remember this is the sum of the first n terms. So if I want s sub 8, that's the sum of the first 8 terms. And when you look at this summation notation, that's coming right here. That's where I'm stopping. So n is equal to 8 in terms of that formula. Okay, in terms of other things, if you want a sub 1, again, if it matches up here, again, forget about the letters. If things match up, if this is I minus 1, that matches up with n minus 1. This right here would be your r. And then this right here would be your a sub 1. Now, there's a little word of caution that I'm going to give you, and you're going to see examples like this on the practice test. You will not always be given something in the form of I minus 1 for your exponent. Sometimes it'd be I, sometimes it'd be I plus 1. You might have I minus 2 or something like that. So you have to figure out how you're going to get a sub 1 in that particular case. I'm going to leave that for the practice test because I want you to think about it on your own. But really, it's quite easy to rewrite it just using the rules of exponents. But for right now, we do have something that matches up. So your a sub 1 is just going to be 3, and then your r is going to be negative 2. And again, you can see that because if I plugged in a 1 for I there, 1 minus 1 is 0. Negative 2, again, to the power of 0 is 1. So you get 3 times 1, which is 3. So what is the value of this sum in here when I is equal to 1? Well, it's going to be 3. So again, that's your a sub 1 value. Okay, so coming down, now we're just going to plug in what we know. So a sub 1 is 3. So let me highlight that. So that's going to get plugged in there. And then we know that r is equal to negative 2. So that's going to get plugged in there and then there. And so that's going to end up right there and then right there. Now, again, the n value, like I talked about earlier, is going to be from that upper limit of summation when it's written that way. So I'm going to put a comma here and just put that n is equal to 8. Sometimes your problem will just be given as what is s sub 8. And in that case, it's a little bit more straightforward. But with a summation notation, you have to think about it. So this right here is going to get plugged in right there and then also right there. So see, we have this s sub 8 here and your exponent here is an 8. Okay, so once you plug in, you can just key this into your calculator. So I'm just going to tell you s sub 8 is equal to negative 255. The intermediate steps are right here if you want to pause the video and look at them. But I think pretty much everyone's using a calculator at this point. So s sub 8 is just equal to negative 255. All right, let's finish things up by talking about the sum of the terms of an infinite geometric sequence. This does involve the concept of limits, which is something you're going to study in great detail when you get to calculus. For right now, we're just going to do the basics. So we have something like, let's say, s sub 4 that we know how to do at this point. So this is just equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and then you stop. So you sum those 4 terms, that gives you your s sub 4. Well, what if I didn't stop? In other words, this is a sub 1, this is a sub 2, this is a sub 3, this right here is a sub n. So if I go through and say I want a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus, again, the pattern continues, plus you have your a sub 1 times r raised to the power of n minus 1, then plus I continue after that. So I'm not going to stop. In other words, with s sub 4, I stopped, but now I'm just going to continue. So in order to deal with that situation, we take our formula here that we talked about previously, and we're going to modify it for a very specific scenario. So if the r value, again, the common ratio, is greater than negative 1 and less than 1, then what's going to happen is the limit as n approaches infinity of this r raised to the power of n is going to be equal to 0. So let me stop for a moment because, again, we have not talked about limits very much. We touched on it earlier in the course, but all you're thinking about here is what happens to r to the power of n as the n value gets larger and larger. Well, it's getting closer and closer to 0. So as a simple example, suppose you have 1/2, so that's an r value that's greater than negative 1 and less than 1, and it's raised to the power of n. So just matching this right here. So if you plug in a 1 for n, well, you just have 1/2. As a decimal, it's 0.5. If you plugged in a 2, you'd have 1/4, which is 0.25 as a decimal. If you plugged in a 3, you'd have an 1/8, which is 0.125 as a decimal. If you plugged in a 4, you'd have 1/16, which is 0.0625 as a decimal. If you plugged in a 5, you'd have 1/32, which is 0.03125 as a decimal. If you plugged in 6, you'd have 1/64, which is 0.015625 as a decimal, and so on and so forth. So you're going to keep getting closer and closer to 0. You'll never actually get there, but you'll get closer and closer to 0. So that's why we say the limit as n approaches infinity of this r raised to the power of n is equal to 0. Now what we're going to do is we're going to make a little substitution in our formula. This right here is your r to the power of n. That's going to be replaced with 0 right here because of this right here. So the limit as n approaches infinity of s sub n is equal to a sub 1 times the quantity 1 minus 0. And again, the 0 is coming from us replacing this right here with 0 because of this right here. That's all we're doing. Then this is over 1 minus r. So when you think about this, this just becomes a sub 1 because 1 minus 0 is 1 and 1 times anything is itself. So it's just a sub 1 over 1 minus r. So we can say the quotient a sub 1 over 1 minus r is called the sum of the terms of an infinite geometric sequence. So this is your formula right here. You might see it with summation notation. It's the same thing. So s sub infinity, so you're going to keep summing the terms, is equal to a sub 1 over 1 minus r. And again, this is valid when r is greater than -1 and less than 1. If the absolute value of r is greater than or equal to 1, the infinite series does not have a sum. I'm not going to really go into detail on this. This is something you're going to talk about when you get to calculus. But if you get a question like that, you could just put that it doesn't have a sum. All right, let's look at an example. So here we have the sum as k goes from 1 to infinity of this -4/3 times 1/5 raised to the power of k minus 1. So again, if you look at your a sub n is equal to a sub 1 times r raised to the power of n minus 1. In this particular case, if you match things up, well, a sub 1 is going to be -4/3 and r is going to be 1/5. And again, always be careful of this right here. Just make sure this matches what you have right here. I know the letter is different, but it doesn't matter. This is k minus 1, so if you plugged in a 1 here to get the first term, so 1 minus 1 is 0. 1/5 to the power of 0 is 1. So this would go away because multiplying by 1 doesn't change anything. So you just have -4/3. So that's your a sub 1 value. Okay, so now that we know that a sub 1 is -4/3 and r is 1/5, again, because 1/5 falls in the category where it's greater than -1 and less than 1, we can use this formula. So s sub infinity is equal to, you're going to have your -4/3 being plugged in for a sub 1 over 1 minus, you're going to have this 1/5 being plugged in for r. And actually, let me highlight this so this is more clear and highlight this just so the colors correspond. So this is something we can simplify pretty quickly. Since we have a complex fraction, you can multiply the numerator and the denominator by the LCD, which would be 15. And of course, if you have -4/3 times 15, then 15 divided by 3 is 5. -4 times 5 is -20. And then for this part right here, you would have 15 times 1 and then minus 15 times 1/5. 15 times 1 is just 15. And then minus, this would cancel with this and give me a 3. So 3 times 1 is 3. So 15 minus 3, and this 3 is terrible. Let me fix that. So 15 minus 3 is going to be 12. So what you end up with is -20 over 12. And if you simplify that, you can write this as -1 times 5 times 4 over this would be 4 times 3. And we'll cancel this 4 with this 4. So this equals -5/3. So that's where that's going to come from. Now I'll go back up and just write this with the summation notation. So I'm just going to say that the sum as k goes from 1 to infinity of this -4/3 times 1/5 raised to the power of k minus 1, and that's going to be equal to -5/3.